I have a tough spot because it's the last talk before lunch, and we're in Italy. The food is going to be great. Everybody's hungry, so I'm going to do my best not to make this boring. Another thing, this thing has a lot of demos in it, so a whole ton of things can go wrong. Maybe you've seen this Netflix series, Trainwrecks. This might be one of them. So we have a bunch of demos, a lot of things can go wrong. And one more thing, who here is a Swift UI developer? Okay, I have a demo that might be offensive to all of you, so wait for that as well. So we're in for a wild ride. I want to take you on a journey that I've been on for about the past year. And that's the journey to kind of understand how AI actually works. So all of us have been, in one way or another, affected by AI, right? We might use AI coding tools, we use AI to look things up, to understand how stuff works, generate pictures or whatever. And I think we all have sort of, kind of an understanding of what some of the terms mean, like what a model is and what maybe training means and what inference means, or what it means that a model has a certain number of parameters. But at least for me, I didn't really understand what all of that means. So if you are like a computer scientist and have studied like data science and machine learning, you can go to lunch early because you're not going to learn anything. But if you're just a normal software developer like me who wants to understand how things work, then stay. And hopefully, by the time lunch begins, you can walk away with a deeper understanding of how some of this stuff actually works. And we're going to keep it exciting. There's going to be history in this talk. There's going to be math in this talk. There's going to be code, a lot of code. There's going to be intrigue, no, integers. So let's get started. And I already got my introduction. This is this old picture from 18 years ago at my first WWDC. Young lad, you have so much to learn. But yeah, I've been doing software development for a while, and currently live in Berlin with my lovely wife, who's in the audience today. One person who will clap, which I'm happy about. And yeah, I do freelance work, iOS, full stack, and also AI. But let's get to the interesting stuff. So we're going to talk about what a perceptron is. We're going to build one in pure Swift. We're going to train it, and yeah, do all of that in pure Swift. So first of all, what is a perceptron? This is part of the history part. A perceptron is the first artificial neuron that was actually implemented. And this happened a while ago in the 1950s by Frank Rosenblatt. And in the background, you can see that this thing actually filled a room. It was implemented in hardware, and it filled a room. And in 1958, there was an article that Frank Rosenblatt wrote about the design of an intelligent automaton. And he said, introducing the perceptron, a machine which senses, recognizes, remembers, and responds like the human mind. Impressive, maybe a little early for such bold claims back then, but it definitely sent us on the path of where we are today, where we actually see a lot of these statements being true. So at the core, a perceptron is something that can take multiple inputs, do a calculation on them, and produce an output. And the way the perceptron works is, it's a binary linear classifier. That means if you have a data set that can be divided somewhere in the middle, where some data falls on one side of the line and some data falls on the other, based on certain criteria, the perceptron can find that dividing line. And then when it gets new data that it hasn't seen before, it can decide whether it falls on the one side or the other side of the line, and then make a prediction. As an example, the dots that you see here on this chart are from the publicly available iris data set. The iris is a kind of flower, and this data set has different criteria of these flowers. And one thing you can measure is the sepal. I never knew this existed, but that's what it is, the sepal. And in this data set, you have the width and the length, for example, of the sepal. And the interesting thing is, when you take the width and the length and you chart it on a graph, you can actually see that you can draw a dividing line and then decide whether it's versicolor or setosa, two different kinds of the iris flower. So if you go for a walk and you come across an iris flower, you could measure the sepal, plug it in, and then based on those numbers, the perceptron could tell you if it's either the setosa or the versicolor, as one example. Let's take another example. Imagine you work in a hospital, and you have maybe years' worth of charts of patients who have been dismissed from the hospital. And you have data like maybe their age, their gender, their weight, how much time they spent at the hospital. And then in the last column, you also have the data if within a month they were readmitted because they weren't really well yet. With the perceptron, it's possible to train on this data, and then the next patient that comes in and is about to be released, you could plug in their vitals, and the perceptron could tell you, you know, he's going to be readmitted within a month, so maybe just keep him a few more days. This is the kind of stuff that the perceptron was capable of, learning from data and then making predictions on unseen data. To put it differently, and you will notice this in this talk, sometimes I will explain the same concept multiple ways because that helped me to understand. So I'm still a learner, and I'm basically just sharing with you what helped me to understand and learn some of these things. So before the perceptron, basically the way computers were used was you put data in, you processed the data, and you got a result out. With the perceptron, instead of getting a result out, you really got a program out. Because the perceptron could learn from data, really produce a program, and now into this program, into this trained model, you could plug in new data and then get a result out. So that's kind of what the groundbreaking thing was. So in connection with this, we want to see how does a perceptron actually make a decision. We'll get to the training part later. First, we'll look at how does a perceptron actually work internally and make a decision. And two things that are important for that are weights and biases. Weights, if a perceptron has multiple inputs, let's say the width and the length, so two inputs, then it will also have two corresponding weights that basically say how important each input is in the calculation. And then it also has a bias, which is a fixed term that basically says how high the threshold is for a value to have to jump over to get either into the one camp of data or in the other camp of the classification. I like to think of it as a limbo. So basically the weights dictate the slope, how much the line is tilted, and the bias tells us how high the line is that the value has to jump over. Another way that I like to visualize it is knobs. Let's say you have a sound panel and you have multiple knobs that you can turn for each input. Maybe you have two microphones, an electric guitar and a bass, and the weights are like these knobs that can turn the volume up and down on each input and have an effect on the output. So how does the calculation inside of the perceptron actually work? What is it doing inside of this artificial neuron? The first thing that happens is the dot product is calculated. That means that each input is multiplied by the corresponding weight, and then those values are added up. So in this example, let's say we have input 0.7 and negative 1.2, and we have these two weights, multiply them, add them up. That's the dot product. The next step is that the bias is added. It's just added. That's all there is to it. And that's basically this threshold that the number has to go over. And then the last stop is a so-called activation function, which just looks at the result of the previous calculation if it is greater than 0 or not. And then it outputs either 1 or -1. And I had to look up why doesn't it just output 0 or 1? It just makes the following calculations easier when you don't have 0 as a result, but it's more balanced if you have -1 and 1. And that's the result you get. So it's a very simple calculation inside of the perceptron. And of course, this is a demonstration with 2 inputs. This could be 200 inputs or 2,000 inputs, right? And it would work the same way. Let's look at this. First demo that can possibly go wrong. So I have completely vibe coded this thing. So I didn't write a single line of code myself in this program, and I called it Perceptron Viz, as in visualizer. And here on the left, let me zoom in a bit. Whoops. We have data, and in this case, it's a very simple data set for the AND gate. So only when both inputs are 1 do you get a 1. Otherwise, if one of them or both are 0, you get a -1. And then over here, using Swift charts, we have a chart that draws these different dots. So we see here negative and positive, and we see a dividing line. And then if I go down here, we can actually play with the weights. So it's very simple. We only have 2 weights. And we see how this dividing line changes. And we can also play with the bias and see how the tilt doesn't change, but where the dividing line goes changes. Okay, we also have some other data sets. This is the iris flower data set that we looked at earlier. So we have the sepal length and width. And then red is setosa and blue is versicolor. So we can see it's a data set where a dividing line can be found. And of course, the perceptron only works with such data sets that can be divided. And these are very simple because they only have 2 inputs. And as I said, it also would work with 3 inputs. Then it would be a dividing plane, or with 4 or more inputs, which we cannot visualize anymore. But still, the perceptron also works in 100 or 500 dimensional space. And one more, let's look at this one. This is the offensive data set for Swift UI developers. So we have numbers of hours it took to develop a feature and the number of bugs that you have. And let's just say this was for early versions of Swift UI, okay, to keep it down. So and then we can kind of change the tilt here too, you know, and we can see, okay, we have a dividing line, and then let's say we have an unknown feature, and you ask the developer, so how long did it take you to build this? And he said, okay, it took me 4 hours. And how many bugs does it have? Well, let's say it has 20 bugs. You're like, oh, okay, then it must have been developed with Swift UI. Early versions, okay? Okay, so we have it visualized, but now let's look at code. So for me, at least, I can really understand stuff if I actually see it in code in a language that I understand. So right here, we have a playground, and all of this code will be made available to you afterwards. So let's look at our perceptron here. Can everybody kind of see this? I'll zoom in a bit. It's a simple Swift struct. It has an array of weights and 1 bias value. And the prediction function simply calculates the dot product. It goes through all the weights and then multiplies each weight with each corresponding input. then adds the bias value, and then does the activation, see if it goes over 0, and then outputs either 1 or -1. And that's it. And so right here, we have not given it any weights that make sense. We left it all at 0. And if I run this, please work, yes. We see the prediction is wrong for all first three, right? These should be negative, negative, -1. The last one is correct. If I now manually set the weights to something that works, so, if I kind of change the knobs and I run it again, now it's correct. Whoops, -1, -1, and 1. So that's basically how a perceptron works. It's very simple math. The interesting part now is, though, how do we train it? Because none of us would want to fiddle with these values. If it's just 2 inputs, you can actually kind of come up with the weights yourself if you just try long enough. But imagine you would have 100 or 1,000 knobs to turn. It would be humanly impossible to come up with the right combination, right? And so how do we train a perceptron? Let's get back to the slides. Training. Here's some more math. So if we look at our input data set for the AND gate, very simple. The first thing we do is set a so-called learning rate. And maybe that's something you've also heard before if you kind of read some AI stuff. For example, point 2. Learning rate just means how big the adjustments are going to be that we make in each iteration of the training cycle. Then we set a maximum number of epochs. An epoch just means how many times are we going to iterate over the data set before we stop. And we stop either when we get everything right, or if we don't get everything right, then if the maximum number of epochs, of iterations over the data set is reached, we're going to stop training. Then we initialize the weights and the bias to random values. People might ask, well, why don't we just initialize them all to 0? That's possible, but you get better results and quicker and more quickly get to the desired training outcome if you start with random initialization. Then you iterate over the training data and you make a prediction. So you use the 2 inputs, you stick them into the perceptron, make the prediction with the current set of weights, and then see what comes out. And you compare it with the expected output, right? So if we, for example, for the 4th row, if we expected an output of 1, but we got -1, then we calculate the error. So we do 1 minus -1 is 2, and then we use that error to update all the weights. So the calculation is simple. We take the old weight plus error times learning rate times input. So in this example, 2 times 0.2 times 1, for example. And that's the new weight. So we update the weights, and then we go through the training data set again, and we try again. And exactly, we continue. So the idea of training is it's tiny nudges to reduce the errors in our predictions. So to zero in on the best results. Let's look at that. So in our Perceptron viz, we can reveal a training section. So in our training section right here, we have a few settings we can set. The maximum epochs, a pause for dramatic effect, so we can actually see what's happening, and the learning rate. So we have a learning rate of 0.1. And let's look at our simple data set, the AND gate, right here. And I'm just going to set this to something sort of random. and I'll say start training. So now we see it goes through the data set, it makes predictions, and we see at first that it makes several mistakes. And if we look here, after a while we see the line kind of coming into view, and it's trying different things, and it's slowly zeroing in on where this line should be. And there we go. And we see here that this line could be in multiple places for this example, because we have a lot of blank space between our data set, and it's a super small data set. And we can now try it out. So if I put in input of 0 and 1, it comes to false. And if I put in 1 and 1, it comes out to true. So we successfully trained a perceptron to make a correct prediction. And if we reset this again, and I go back to something that's kind of wrong, say here. If you download this later on and you want to play with it yourself, you can also step through it. And when you step through it, the whole training updating calculation is laid out to you. So the weight 1, the old value plus the learning rate times the error times the input as the new weight. So you can kind of step through it and really see like how it kind of zeroes in on the correct values. Okay, let's look at that in code. So if I go back to my Xcode playground, and I kind of zero this out, we have our data set up here, the AND gate. We also have one for OR and another one. The perceptron, the prediction function is the same that we already saw. And now let's look at the training. So for the training, we put in the data set that we want to use to train it, our learning rate, and the number of epochs. We simply iterate over the epochs. We take the inputs and the expected output of our data set, and we make a prediction. And then we see, did it make a mistake? Was the prediction correct or incorrect? And we calculate that by subtracting the prediction from the expected value. If we did get an error, we iterate over the weights and make the calculation that we just saw on the slide. We take the old weight and we add error times learning rate times input. And we do the same for the bias. And since the bias is a fixed value that does not depend on an input that we put in, it's just multiplied by 1. So we could also leave this off, of course, but just to demonstrate that this is its input, so to speak. And then we keep doing that until either we get everything right or we run out of epochs. So if I run this on the AND gate dataset, we see right here, first epoch, it made 2 mistakes. Second epoch, also 2 mistakes. Third one, 2, 3 mistakes. Fourth epoch, and then finally it gets less, and then in epoch number 6, it found the correct values. And then it made a final check, said, yep, everything is correct. That's how you train a perceptron. Let's go back to our slides. So now for a little bit more history. It's interesting, the first perceptron that we saw, this huge room-filling machine, was implemented in hardware. And this is a picture from its original user manual. They actually printed a user manual. Maybe they expected people to buy it, I'm not sure. And I was fascinated when I learned that they didn't just plug in numbers, but they actually had a camera as an input in the 1950s. And so the first perceptron was trained on photographs of people's faces. And there was someone who actually sat at a desk, took these pictures of people's faces, and then manually trained the Perceptron. And it had a camera that had a grid of 20 by 20 photo sensitive things that could kind of look at these photos. And then the person would say, yeah, the prediction should be man or woman based on the appearance, and then select wrong or right. And then it could put a previously unseen picture in there, and then output if that's a man or a woman. And it had, I think, a success rate of about 70% back then. So if we think about it, that's 20 by 20 as a grid of inputs. That's 400 inputs plus a bias. That's 400 weights. Our Perceptron can do that, the one we just wrote in Swift. We can train our Perceptron to do exactly what the Mark I Perceptron did. So how about we do that right now? We can take the UTK face dataset, that's an open source dataset, of a lot of faces of people. And it's augmented with a lot of metadata, for example, the age and also the gender. And we can use that to train our Perceptron. So we can take one of these pictures, turn it into 20 by 20 grayscale values, and that's really 400 inputs into our Perceptron. And we can train on that. So instead of having this table that just has 2 columns, input 1 and input 2, and an output label, forget that. We're going to have a table that has 400 pixels as the input, and then whether it's male or female as the output. Let's look at that right now. So this is the third GitHub repo that I'm going to share with you. It's called Perceptron Face. And if we look at the training data really quick, so we have the UTK face dataset, and here, the first number here in the file name is the age. So age 1, we have a bunch of baby faces, and then if we scroll and scroll and scroll a lot, we kind of get to adult faces. So we have a whole bunch of faces. And if we now look at our code, we have a bunch of code that kind of does the image processing, turns it into grayscale, stuff like that. But if we look at our actual Perceptron, it's the same that we've been looking at this whole time. So it's a struct, we have our weights, we have our bias, we init it with an input size, for example, 400, and it's just going to initialize the weights randomly when we do that. And we have our prediction function, which is, again, the same thing that we've seen. The activation function that looks if it's over 0 or not. And then we have our training, which also does the same that we've done before. We have our epochs, we make our prediction, we calculate the error, we update the weights. And in this case, it's 400 weights plus a bias that we'll update. And let's train it. Let's see what happens. So if I do, let's train it with 100 epochs. Okay. So it's first doing the pre-processing. This is the initial weights. And we see it makes 1,861 errors. So we take a data set just, I think, between the ages of 25 and 35 or something. And that comes out to about 6,500 images. So with each epoch, it goes over those 6,500 images. And we see here's the learning rate. We have a little tweak in our code that it actually reduces the learning rate as it keeps going, so that it makes smaller and smaller adjustments as it keeps going. And now we're up to an accuracy of 89%. And then at the end, it kind of outputs a few tests. Let's look at that. Predicted female, actual female, correct. Predicted male, actual male, also correct. And also female, female, correct. Okay, So now the interesting part is going to be to try it on previously unseen pictures. And I took the liberty of taking some pictures of our fellow speakers. So let's try it out. And please, if it gets something wrong, this is AI. AI can make mistakes, okay? This is not personal. So we're going to see if we can, let's start with speaker 1. Male, prediction male, correct. That's good. Okay, speaker 2, that's Claire. Please, Claire, don't kill me if this is wrong. Female, yes, it worked, it worked. Okay, we have one more, or two more, Chris. Chris, he doesn't live too far from me. I'm in Berlin, so I might be in real trouble with this one. Male, also correct, and we have two more. Ekaterina. And female, correct, and Klaus. Okay, we're also going to do Klaus. He's never going to invite me again if this goes wrong. Male, all right, so that worked as well. Okay, let's go back to the slides. So let's do a quick recap, okay? First of all, you've learned now how one of the most basic building blocks of modern AI works. An artificial neuron, the Perceptron, and it's still being used today. So if you use frameworks like PyTorch, you're going to come across something like an MLP, multi-layer perceptron. And the power that comes from that is that you can chain them up, right? You can use multiple perceptrons and then use the outputs of those perceptrons as the input of the next layer, and so forth and so forth. So it's still relevant today. So it's a binary linear classifier. Weights means how important each input is. The bias is the threshold that a value has to go over to be classified either in the one camp or in the other. Training means tiny adjustments to reduce the error. So predict over and over again and make tiny nudges, tiny tweaks. The model can actually mean two things. Model, on the one hand, can mean how neurons are connected, kind of the blueprint, the architecture of how different things are connected. But often the word model is also used for the weights and biases after training, right? And so, just to go over to this slide one more time. So here in this thing, we have now a weights.json file. So really, this is our trained model, right? We saved the bias and the 400 weights that we trained into a JSON file. So this is our trained model that we just trained. So the weights and the biases after training. So if you use Olama or a tool like that and you download like a 3 GB model, that's really the weights and the biases that you download, the trained values that came after training. And parameters is the amount of learnable weights and biases. So our very first model that we looked at had 2 inputs and 1 bias. It was a 3-parameter model. So if you download a 7 billion parameter model, that means it has 7 billion weights and biases that can be learned and trained. And in our last example, we created a 401 parameter model, 400 weights and 1 bias, right? What helped me a lot on this journey, that I'm still on, to learn and to understand how this stuff actually works on the hood, is this wonderful book, Why Machines Learn, The Elegant Math Behind Modern AI, by Anil Ananthaswamy. I hope that was correct. It's a great book. It's super interesting to read. Also has a lot of the personal stories about the characters that shape modern AI, and it really helped me to understand a lot of things and not understand other things. So I definitely have to reread it. And another book that I'm currently reading is Build a Large Language Model from Scratch. So you actually build a GPT-2 style model from scratch using this book, and I hope that it will enlighten me a bit more. And I want to close with one appeal to please keep learning. While I was reading that book, it was fascinating to learn about people like Frank Rosenblatt or McCulloch and Pitts, and people who came up with this stuff, right? And we have AI tools right now that you can just tell them what to do, and they write a program for you, and they figure out a problem for you. And that's amazing. That's wonderful, helpful. I love using it. But what I don't want to let happen to myself is to stop learning. I still love engineering. I still want to understand how stuff works and have the joy of figuring something out and doing something. And I think that's just my appeal to you. Don't let AI do everything for you, but keep learning, keep exploring, and keep coming up with amazing things. And on that note, enjoy your lunch. Thank you very much.
All right, thank you very much. So we have some time for some question. I love that you had on the slide before the books an optional. I also want to emphasize about the keep learning. Please keep learning languages in the future, even though your AirPods will translate them, because learning languages is about learning the culture, for example. Any questions?
Yeah, I have one. Thank you. Very fascinating talk. And I have semi-random question. Why Perceptron is codable structure instead of class?
Come again?
Why Perceptron in your code is codable structure and not a class?
Oh, that's a great question. I think in the last demo, in order to also persist it to disk, to kind of save the learned weights. And I try to prefer structs whenever I can to classes, but you could totally implement it in a class as well.
So it's an elegant solution. You, at the end, just save instance as JSON, and nice.
Yeah.
Thank you.
Yeah, thank you.
All right, next question. I also, I was not so sure about Klaus being male because I think it's a LLM. But since we are in the subject still, any question on AI or whatever else, or beer? Or looks like everybody's pretty hungry. Catch this guy during the breakfast, not the breakfast. Why? It might be good, but no, during the lunch, and have a wonderful lunch. See you later.